Hello everyone. We are starting a free open lecture in our Discord. All our lectures are held weekly without breaks. If you, the viewer, want to ask questions and receive answers in an online format, join our lectures. You can find the link to Discord in our Telegram channel. To find out the schedule for the lectures, join our Telegram channel. And now let's try to approximately estimate the minimum and maximum depth of such a tree. That is essentially the height from the root to the deepest leaf, as it can be. Well, obviously, since we can have bamboo, the maximum depth of the tree is n, where all the elements just go one after another like this. This is actually very good indeed, because a list will always be better than a heap. We end up with a sorted list according to the rules of the heap, because here we have some value v1, here v2, and according to the rules of the heap, the value in the parent must be less than or equal to the value in the child. And then the delete operation, for example, will be executed instantly in one unit with the algorithm. This is actually a very good case. This is the maximum. Now let's try to estimate the minimum height that can be in this tree. How do we achieve the minimum height? Well, we need to try to make the tree as minimal as possible. Well, let's try to create a minimal tree of rank 0. It will be just that, exactly as it turns out. Minimum tree of rank 1. If I create a minimum tree of rank 1 like this, then I will definitely have some child here. And if I place a star here, then this child will no longer be here. Instead of a depth of 2 nodes, I will get a height of 1 node, slightly. Now let's consider a tree of rank 2. Well, again, it is already obvious that we should use stars. Because the fewer nodes there are, the better it will be. It has accordingly one child, and what will this one child be? Well, let's set it to 0, or we can also use 1 with a star. Here we have a height of 1, here we will have a height of 2. Now let's draw a tree of rank 3. Well, again, it will be 3 with a star, obviously. At 3 with a star, there will be 2 children. The first one, well, 0, it is clear that it fits here. Here, our rank should be greater than or equal to 1. Therefore, we should place the minimum tree of rank 1 here. This is 1 with a star. So, here we have 3 nodes and the height is also 2. Now let's basically create a tree of rank 4. We will essentially draw a spike with a star, of course. Definitely. Here we should have 0. Here we should have 1 with a star. And here we will have 2 with a star. Here we already have a height of 3. And so on, it will continue. In this case, for example, as you can see in this scenario. So how can we evaluate the height after all? We are still dealing with binomial trees. They are slightly different, but in structure they are also binomial. In a binomial tree, what holds true? If n is the number of nodes in the tree, then the number of nodes will always be less than or equal to 2 raised to the power of k, where k is the rank of the tree, and in a binomial tree, this height is also k. Thus, there are k children and the height is also k. Heels are probably the best k.
Want to become a great programmer? Subscribe to our Telegram channel.
Here we actually have fewer children, but they grow a bit differently. Let me replace the fabric after all, because we are looking for height. There. From here we have some estimate for h in the binomial tree. We just need h from here. To express this, it is a logarithm. This means that h will be greater than or equal to the logarithm with base 2 of t. This is in binomial trees. How can we evaluate this? Well, we won't be able to assess the height in this way. We'll have to draw it, but we can find some relationship regarding the number of nodes. Let's count the number of nodes in each tree. Here we have 1 node, here also 1, here 2, here we have 3 nodes, and here we have 1, 2, 3, 4, 5 nodes. Attention, question. How many nodes will there be in a binomial tree of rank 5 if we compress it to the maximum? What is the minimum number of nodes in a tree of rank 5? Here we see the Fibonacci numbers. In fact, they can be noticed right here. Let's try to understand why autumn is taken into account at all. Where do Fibonacci numbers come from in this context? What does this represent? We very carefully took a tree of rank 1 and then attached to it a tree of rank 0. So we have obtained a tree of rank 2. That is, we have this node positioned at the top. while the tree of rank 0 is at the bottom. Now, what do we have here? We took a binomial tree of rank 2 as the basis and attached a node with the value 1 to it, because here the constraint is greater than or equal to 1. The same story applies to 5s. We take the tree. In the quartet, we take a binomial tree of rank 3. Here it is, and to it, we need to attach another node which will have a rank greater than or equal to 2. Greater than or equal to k2. This is exactly 2, so we take this and also pay attention to the tree of rank 2, and what we end up with is this recurrent form. If we want, let me introduce the function nk, which will represent the number of angles in the tree of rank k, and then we will have exactly this, precisely. What does n of k equal? N of k minus 1 plus n of k minus 2. But what is the essence? Essentially, fundamentally, in essence. Here we seem to have found t in terms of k. If we substitute it here, how can we express it in terms of masha? Because this is a recurrent formula, it's unclear. There is another formula for Fibonacci numbers that is non-recurrent. It involves mathematically rounding the number of the golden ratio raised to the power of a, which will be divided by the square root of 5. And now we can substitute this right here. This will indeed be our exponent. So this parade is our exponential progression. So, what does this mean? It essentially means that our Fibonacci sequence of numbers grow according to an exponential progression. Here we will have not 2 to the power of h, but specifically I to the power of h, in this particular case specifically. And then what will our estimate be? M is less than or equal to e raised to the power of h. Well, we can ignore any rounding constants. There's no point. And then from here, h more precisely. Will it actually be greater than the logarithm to the base of the golden ratio? If anyone doesn't know, phi is a number, 1 plus the square root of 5 divided by 2, I believe. And here we have obtained the minimum height of the tree. And in fact, this heap is actually called Fibonacci because Fibonacci numbers indeed appear in the number of nodes needed to build minimal trees, essentially. And here we have obtained such an estimate of the height. We will need this later. We will simply know that in the worst case the height will be m, while in the best case the height will be the logarithm to the base of phi. And we will try to merge these trees in such a way that our tree is as close as possible to the best case. The worst case is also possible, of course, but we will strive to make it approach the best. It all depends on what we are actually going to do. If we are going to perform deletions, then bamboo is a wonderful thing because we can simply cut it and that's it. We won't need to do anything else. Bamboo is not only easy to cut, but it also grows back quickly, making it a sustainable choice. Additionally, it is strong and versatile, which makes it useful for various applications. If there were a tree here, we would definitely need to take its children and merge them here. Using bamboo would be much more efficiently. Suppose we need to decrease this key, then we would indeed have to ascend up this bamboo. And if it were perhaps a tree, the height would be smaller here. But there is no concept of what is actually better. It just is what it is. So, all right. Well, let's move on to the operation. Now basically, we already know a lot to basically perform these operations. To understand how the heap will be structured, well, we will start classically with the merging operation, because again, it will be through this that the necessary adjustments will be made in this case. But before that, let's first outline how this heap will essentially be stored. This heap will actually be stored as a list of these trees. That is, we have a tree of some rank here, another tree of rank there, another tree over there, and so on. It will go simply as a list. This list is not sorted by rank at all. It's just a list, that's all. I don't know, 2, 1, 3. This is specifically by rank. I won't write the values in the nodes at all. Here the nodes only contain ranks if that matters. Like, well, values that satisfy the properties of the cult. The value of the parent must be the value of the child. We store it in a very straightforward manner. Now, although no, let's start not with the merge, but with the top. That is, how do we obtain the minimum element? We simply take it and remember where it is. Let's say it's in this tree, and we just store a reference to it. Obviously, we will do this for you from 1. We simply follow the link and return this value. Now we can move on to merging two heaps. Here we have a heap. The first one is some kind of list of Fibonacci trees. There is another heap, which is also a list of Fibonacci trees. Here is 1, here is 2. How to merge them for these units? Totem. This is not a heap of lists. I don't want to. Let's go with IP. These reds are the minimum. I showed it once, and that's it. We need to merge them, meaning we have to obtain one like this from this heap. For example, this one is smaller, so we will have the minimum element left here. This is for us without a drop. The length of the list plus just a list. Here at the 0 position is a tree, at the 2nd position, and at the 3rd position is a tree in the list. And here it's the same. At the 0 position, a tree. At the 2nd, at the 3rd. But let's consider, what do we need to do to merge two heaps? We need to somehow quickly combine these two sets and then select the minimum. Let's start with the simplest thing. How do we select the minimum? What will be the minimum result? The minimum of 2. We can select the minimum very easily. We take these values, and the smallest among them will be the minimum. Where do we point the reference? How to merge quickly? Well, yes, but this is not an array, it's lists. If there were arrays here, we wouldn't be able to do this. And in lists, it's very easy to do this. Since these are lists, we can simply establish a connection like this. We link the two ends of the first list to the beginning of the second. We already have this one list, and this other list becomes empty because the data has flowed from it here. We are not copying anything. We are just linking them. We have linked them, and then we simply choose the minimum of the two. This will be our new minimum. This is the merging unit. The merging of lists is ready to operate in C++. This is one method to return everything. Naturally, when merging, we need to remember to empty this heap, meaning we should clear its size so that it automatically transfers everything from here to there, and if needed, we should completely clean it up and mark that there is nothing left here. All the data has been transferred to the heap.
Want to become a great programmer? Subscribe to our Telegram channel.